Hi there, Andrew Dunkley here. Thanks for joining us on a Q&A edition of Space Nuts. And coming up, we're going to answer a question from Ron. He wants to know if we could see a planet that sustains life, would we know it? And vice versa, if there was an alien race out there and they spotted Earth, would they know we are here? Good question. Dean is a bit confused about spheres versus disks. Why does it happen? Why aren't they all spheres or all disks? Anne has a brilliant question, love this one, about bone density in space and some of the problems that are associated with being in zero gravity for long periods of time. And Dean, too, it's not the same Dean, is asking us about centrifugal force. We'll cover all that in this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Here he is again, Professor Jonti Horder, Professor of Astrophysics at the University of Southern Queensland. Jonti, hello.
Hey, how you going?
I'm all right. I got a question without notice.
Yes.
Did you ever sort of have people rib you at school, like Jonti Horner sat in the corner eating his Christmas pie, down came the comet that made Jonti vomit, and now he only eats flies?
Oh, that's brilliant. That would have been far more pleasurable than my actual school experience. It's probably not worth getting into too depressing a thing, but up until I went to university, I had a horrendous time at school because I grew up in a very working class area, low socioeconomic area with hugely high unemployment during the miners' strikes in the 80s. And I was an only child, so I'm not necessarily blessed with the best social aptitude, particularly at that age. But I was smart enough to be very smart, but not smart enough to realize that there are the right way and the wrong way to go about that. So I had a horrible time for the 12 years at school in terms of bullying. I was catastrophically bullied, but it made me who I am today, so I'm not going to complain too much about it. But yeah, it's the curse of having aspiration and the curse of being smart in an area where that wasn't a common thing. A lot of empathy for the kids I went to school with, because you're talking about an area where many of them didn't have any family members who were employed because of what was going on. There was a huge epidemic of men taking their own lives because of all the things that were going on. So it was a pretty rough time, a pretty rough place. But such is life, unfortunately,
Yeah. Well, I certainly had my share of bullying at school, and not often, wasn't an everyday thing. It was, I suppose, looking back, reasonably rare, but it never sits well. It's a horrible thing.
At least these days, nowadays, there is more being done to counter it and more awareness of it, because, the impression back when I was at school was you just needed to man up, which is an awful phrase, and everybody has to deal with it. It's a formative experience, and teachers couldn't care less. As long as you weren't getting knifed or something, they weren't interested.
I used to talk to my boys about it and ask them how they were going, and they always said, no, we never had any trouble, but then teachers would tell me otherwise. So they're obviously not keen to talk about it. But my middle son, who was always very tall through school, he towered above all the other kids. I think he was the second tallest kid in his year and in the school in general. And I said to him one day, do you get bullied? And he went, no, because he was big. He was a big kid, and no one went near him. So his height was actually a good defense mechanism. It's funny how it works out, but that says a lot about anthropology, I suppose. When we're not talking about
it's all interesting about the ages in which kids develop awareness of self and the ages at which they develop empathy and kindness and all those kind of things in a specific sense rather than a general sense. It's really interesting.
Yeah, it is. All right, let's deal with some questions. And our first question comes from Ron. He said, if scientists in a distant solar system were searching for exoplanets using the same technology that we're using, and if they were to observe our planet, would they be able to tell with any degree of certainty that there was life here? Or conversely, if we were to observe an exoplanet that's exactly like Earth, teeming with carbon-based life and perhaps with an advanced civilization modifying their atmosphere, which we talked about in the last episode.
Yeah.
Could we tell that there's life there? Thanks, Ron. Great question, Ron. We've had questions like it before, but I just love this topic. So, yeah, we'll do it again. And Jonti hasn't had to answer this one before, so I thought it'd be interesting to get his take on it.
It is, well, it's a fabulous question. And I mean, the sad answer is we're not quite there yet. So if we were looking at the solar system from around another star, depending on which method we use, we'd be able to find Jupiter and probably Saturn, but we'd have to observe for a very long time to measure the wobbles for them. So we'd need to observe the sun for a decade or two to pick up Jupiter and Saturn. Everything else we wouldn't be able to find. Now, if we had something like TESS, the Transit Planet Survey satellite, looking at our solar system, there's a very small chance it might pick up the Earth or Venus, but TESS typically only looks at stars for 27 days. The Earth takes 365 days to go around and would take only 16 hours to transit, so the odds of catching a transit are pretty much nil. So we're not there yet. We are getting better, and as we talked about in the other episode, we're getting to the point where we can find planets that are a bit bigger than the Earth, but on orbits that are comparable to the Earth around stars like the Sun. We can find planets smaller than the Earth around dim little red dwarf stars using the transit method. But that's partly because those planets are so close to their stars, they're going around really quickly. So the upshot of all that is if we were orbiting another star looking back at the solar system, I think we could only confidently detect one or two planets. The Earth would probably be the third planet that will be discovered as the technology got better, because it's the biggest of the terrestrial planets. But it would depend a little bit on your line of sight, because the terrestrial planets are all slightly tilted to each other. So if you're going to find them through the transit method, the likelihood is only one of them will transit and the others won't. In the radial velocity method, you'd pick out Jupiter and Saturn, but you'd struggle for anything else. Eventually you'd get there, but you'd need technology a bit better than ours. So we're not at the point of finding the planets yet, never mind finding the life on them, but that's like the next step in the journey. We've only had 30 years of the exoplanet era. We're only in the first few decades of being able to do this at all. And the progress we've made is utterly astonishing. And I think within the next decade or two, we'll routinely start being able to find planets that are Earth-sized on Earth-like orbits and to start looking for evidence of life on them. But that is going to be the hardest observations we've ever had to carry out. In terms of detecting life like us, though, it's a slightly different proposition. So finding any evidence of life is going to be challenging. So people often talk about biomarkers.
Yeah.
Which is this concept that there are certain things you could look for that would be indicative of life. And we've talked about the possible detection of phosphine in Venus atmosphere before. We've talked about stuff like the chicken soup experiment the Viking landers did on Mars in the 1970s, where they dug up some soil and put some soup on it and saw if it gave off gases, because there could be life there using the nutrients. When you're looking at planets around other stars, there is no guarantee that life on those planets would have followed the same evolutionary pathways as life on Earth. So a lot of the very specific biomarkers people propose are based on our knowledge of life on Earth, because it's the only planet we know does have life, and it's the only example of life we've got. One of the examples here is something called the red edge, which is when you look at the spectrum of light from a planet, if the planet has a lot of plants on board that are using chlorophyll absorbs incredibly strongly in the red, so you might see a feature in the red that is the signature of chlorophyll, and that will be an indication of plant life. The problem is, and again, I'm not a biologist, so there's probably more to this than I'm going to say in my simple version, is that chlorophyll is an incredibly efficient compound for allowing plants to utilize light like the light from our sun. But there are many other compounds that could do a similar job for stars of different temperatures that are therefore different colors, so they put out the bulk of their light at slightly different wavelengths. And there's no guarantee that life on another planet would use chlorophyll, especially if that star was significantly different to the sun. So the specific biomarker of the red edge from chlorophyll wouldn't work very well necessarily. It wouldn't be guaranteed to work, especially because it's also mimicked by the spectrum of olivine, which is a very common mineral, has a very similar appearance. But looking more generally for that kind of absorption feature in the spectrum that you can't explain any other way is one of the signs people would look for. So it's not so much a case of looking for a specific thing, but rather for looking for something that is out of place, trying to explain it and finding that the only explanation left is life. you're looking for something out of balance. So another good example is on Earth, we have oxygen, we have methane. Now, there's a lot of oxygen in the atmosphere, but that doesn't necessarily mean life because there are chemical processes that can produce oxygen without life being involved. Similarly, with a lot of methane in the atmosphere, and methane is a natural product of animal life. I know my dog lying next to me has been quite happily producing methane through the podcast because we fed her some broccoli, I think, in a puppy food last night. So methane is produced by life, but there are also lots of natural ways it can be produced. And, there's huge amounts of methane in the atmospheres of Uranus and Neptune, for example. So finding oxygen or finding methane doesn't necessarily mean life. There's a lot of other explanations. But the oddity with Earth is that we've got oxygen and methane together. Now, when you put oxygen and methane together, they react with each other a lot, and they react until all of one of them is gone. So the methane in Earth's atmosphere has a really short residence time of only a century or a few centuries, I think 400 years maybe, before it's all gone. So you look at the Earth and it's got oxygen and methane together, which means something has to be producing new methane to replace the methane that's lost. Now, even that doesn't mean it's life because volcanoes produce methane. So what you then have to do is say, well, this is interesting and it could be life, it could be something else. Let's measure the methane over time. And if it's volcanoes, you'll get the methane falling off until at a random time a volcano erupts and there's a spike of methane and then it falls off again. At a random time later, you get another spike. But when you look at methane in the Earth's atmosphere, it varies with the seasons. Volcanoes don't do that. So therefore, that's an indication of life. So it's looking for that oddity that's out of place. There are a couple of things that would give away arguably technologically developed life, which doesn't necessarily mean intelligent life, as we're seeing in the political sphere at the minute, but technologically developed life. One of them is chlorofluorocarbons. So the things that we were putting up into the atmosphere that devastated the ozone layer.
Yeah.
We only know of those being produced by technology. There is no natural process that seems to produce them. Another is radio broadcasts. So any intelligent aliens within about 80 light years of us, 90 light years of us now, would see our broadcast. Now, the exact date of the first broadcast that we sent out that was strong enough to be detected from around the stars depends who you talk to. It could have been the Berlin Olympics in 1936, I think, or the coronation of Queen Elizabeth in 1952, I think the date was. And they're usually held as being the first big broadcast that would have been detectable on an interstellar distance. What that means is that within a certain distance of the Earth, there is a sphere where if there are intelligent aliens with radio telescopes, they could be watching neighbours, and we could well get a broadcast back at some point saying, please stop. We're a bit like toddlers at the minute in a room screaming into the void, and that sound is getting further and further away from us as time goes on. Now, that's the motivation for things like the Search for Extraterrestrial Intelligence, which is helping fund the wonderful radio telescope down at Parkes through the Breakthrough Listen project. The challenge there is that we are already starting to become more quiet. We're like the baby becoming a toddler and moderating itself. And the reason for that is costs. If you were broadcasting in all directions all the time, you've got to put a lot of energy in, and most of that energy is wasted because only a tiny little bit of that is going to get to your receivers. It's much more efficient to send your data, like we're talking at the minute, through the NDN. Through wires or through point-to-point stuff. So the Starlink satellites are a bit like this. They're broadcasting down. Therefore, very little is going back out into space. And anything connecting to them points at the satellite and beams directly to it. So it's much more energy efficient. And there are some arguments that the Earth could well be radio silent again from the point of view of aliens listening in within just a few decades. So there'd only be a short window, and then you've got this shell of broadcasts moving outwards, leaving a void behind it. And unless you tune in when that shell's passing past, you'd never hear us. But in that sense, if we were looking at the solar system with our biggest radio telescopes, we'd probably just about be able to pick up the unusual radio activity if we were at the right distance, but it would still be challenging for us. I think we do have the capacity for that, but it would be hard. So in that sense, if there were aliens around, I don't know, Proxima Centauri b, another of the many, many planets that has been argued has been the most Earth-like ever discovered and made me angry. If there was a planet there, if there were aliens on it and they were broadcasting alien neighbours, we'd be able to tune in.
Wouldn't that be interesting?
Yeah.
So the answer to Ron's question is no, not yet. We're just not quite there. the time may well come, but again, it's needle in a haystack stuff, isn't it?
Absolutely.
Yeah.
Except you don't know what a needle is and you've never seen a haystack before.
Yeah, exactly. Yes. Thank you, Ron. Great question. Lovely to hear from you.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
And our next question comes from Dean.
Hi, Space Nuts. I'm Dean from Washington, D.C. in the United States. I recently started listening to the show and can't get enough of it. Anyways, I was wondering why under gravity do some things form as disks and others as spheres? Where stars and planets are spheres, but some galaxies in our solar system is a disk, but then also planets can have disks around them. I don't know. It's all very confusing. Anyways, thanks. Keep up the great work.
Thank you, Dean. I never would have even thought of that question, and it's a great question. But yeah, he's right. You've got spheres and you've got disks. You've got mixtures of spheres and disks. You've got all sorts of combinations. Why is it so?
It's all down to different physical processes going on. So it's a fabulous question, and we run across this when we're teaching astro and when we're studying it quite a lot. And they are things that happen in slightly different situations. So if you've got material falling inwards under gravity, it will keep falling inwards until either it's moving around on an orbit, so it swings back out. But let's assume it's falling into an object that is going to become a solid or gaseous object, that therefore has some way of stopping that material so it slows down and becomes part of that object. You then have a balance between gravity trying to pull you inwards and the physical strength of the material pushing outwards, if you've got a solid object. If you've got a gaseous object, the gas can keep going in, but then you build up pressure and the pressure holds things up. You might have energy being released that also holds it up. So that then pushes outwards in all directions. I'll talk about solid objects first. This ties into a little bit towards the definition of a planet. There is a concept called hydrostatic equilibrium, which is basically the shape that something that has no strength will finish up in once everything's moved around. You say that it's in hydrostatic equilibrium. It's at the lowest kind of energy state. So if you got outside the Earth's atmosphere, or rather you got away from the gravity of the Earth pulling things down, and you could have droplets suspended, a drop of water that is not moving at all will be spherical. It's held in by surface tension in that case, holds it together, but it will be a sphere. If you rotate it, it will gradually become more elongated and ablate, and it become what we call an ablate spheroid, which is what the Earth is. The Earth is wider at the equator than the poles because of the rotation. And the rotation is essentially applying a slight outward force that means the net force pulling in is weaker at the equator than the poles. And so you stretch out a bit. That's kind of how I visualize it.
Yep.
If you are smaller than a certain size, your material strength is strong enough to prevent things moving around and flowing, so you don't become spherical. You don't get that hydrostatic equilibrium. So if you look at the moons of the planets, the smallest one that I think is in hydrostatic equilibrium is possibly Mimas at Saturn, about 400 kilometers across. It might be one of the other Saturnian moons, but I think it's Mimas. Because that's about the size where you've got enough mass that the gravitational pull is strong enough that that can overcome the physical strength of the material when the object's forming and cause it to then move and flow, and you end up then getting nearly a sphere because that's the lowest energy solution. That's your hydrostatic equilibrium. If you had it being wider than that, more like a block, like an ice hockey puck maybe, but the material can flow, you've got more mass pushing down in the horizontal plane, so things try and squeeze in here and they'll be pushed out that way until it balances out. So you'd end up flowing until you got that kind of spherical shape.
Yeah.
Your ice hockey puck, though, is small enough that its material strength wins, so it stays that elongated shape. So that's kind of the lower end of when people start talking about the definition of a planet, is it has to be in hydrostatic equilibrium. Doesn't mean it's spherical. It just means it's in that lowest energy thing. So if it's rotating quickly, it can be a kind of oblate spheroid. You get a similar thing with stars. So you've got all this gas collapsing in, friction stopping it just orbiting and escaping again. So you've got an object. That object has gravity pulling inwards and it's got a restoring force pushing outwards. In the case of a star like the sun, that's the radiation pressure from all the nuclear fusion going on in its core. Now the sun's rotating, albeit once every 30 odd days, but it is in something that is close to that hydrostatic equilibrium. So if you put a lot of mass on the sun's equator, that would squish in and the poles would push out until you got back to that kind of shape. So that's a physical kind of object. That's why you get them going to be spheres or nearly spheres. It's that concept of hydrostatic equilibrium, and it's due to the balance of the force pulling inwards and the force pushing outwards. Radiation pressure for stars, material strength, material physics going on for solid objects. With disks, you don't have the same things going on. So what you've got is you've got a rotating cloud of gas and dust that isn't really strong enough to hold itself up, but it's rotating quickly under gravity. Now, you've got the conservation of angular momentum going on, so things near the middle go quicker than things near the outside. And there is a tendency for things to collapse down in a disk above the plane of the equator of the thing they're orbiting around. That is due to the conservation of that angular momentum, but it's also due to the motion of things through. You've got all sorts of things coming in. The analogy I often use when I'm giving public talks here involves physics that is different, so it's not a perfect analogy, but it gives you kind of idea what's going on with spinning material. And it's if you've ever seen somebody who's a show-off making pizza bases, they get a ball of very elastic dough and then they spin it around very quickly and whirl it over their head and it flattens out into a big pancake. As a result of the conservation of the angular momentum there, it flattens out into the pizza base shape. And if I tried it, it'd either stick to the ceiling or hit me on the head. It wouldn't go very well. It's a slightly similar thing with the disks of material around planets and stars. Now, what's happening is you've got material collapsing into the star under gravity, forming the disk around it because there is a bit of rotation. With that rotation, as you spin in and you get to a smaller and smaller distance, you move faster and faster and faster. And that's why a gas cloud rotating every few million years gives you a star rotating every few days or every few hours. It's like the ballerina bringing their arms in as they do a spin, they spin quicker and quicker. But that also tends to lead to things collapsing into the plane because that's a bit, again, like the hydrostatic equilibrium example, that's kind of the lowest energy solution. You're rotating around a given rotation axis, you will collapse into a disk in that plane. Material that's coming in above that disk can just carry on orbiting normally. But if there's more material in the disk, there will be friction and it will get damped down and help to collapse down into there. But if the bulk is rotating with the same rotation axis, anything falling in at high angles will probably just fall in and blop straight onto the star. It's rotating that way, but it's coming in here, essentially. Yeah. And I appreciate that description was really useful for the people who are only listening because they can't see me waving my flappy hands around. But if you're coming in from near the poles, the little bit of rotation around isn't helping against you coming in directly towards the target. If you're coming in from the poles and you're going to hit onto the disk, you'll be passing through all that material, and that will damp you down a little bit. So more inclined things will gradually get damped down to add to the disk. The disks we get there for around protostars are material that's falling in, the rotation speeding it up. You get a disk around that protostar. That disk will be a bit flared. It'll have a bit of height because there's a lot of dynamics and stirring and things like that going on. If you could have a big enough region around it, you'd probably end up seeing a disk would eventually flare out until it becomes a background, but you'd have almost cleared lobes above and below the star. And that's kind of what we see with our small body population in the solar system as you go from the planets and the Edgeworth-Kuiper belt going further outwards. You gradually come out towards the domain of the Oort cloud, and when you're far enough from the sun, things get stirred up by passing stars and get put back into a sphere because their tilts are all randomized. So you've got a disk near the sun, and that's because the sun's gravity is dominating, the angular momentum's dominating. When you're very far from the sun, you're only loosely held to the sun, so nudges from passing stars can change your direction quite significantly. And over the 4 billion years since the solar system formed, that material that was flung out into the Oort cloud in a disk, because it was flung out from a disk, has been smeared around, so we now get a spherical-ish cloud around the sun. But when you're close enough to the sun for the sun to dominate, you'd have voids that are fairly empty above and below the plane and a disk low out. So it's all complex, and it's a couple of different bits of physics interacting, essentially.
Yeah, wow. Now, I'd never wondered about it, and I'm glad Dean asked the question because, it really is interesting science. Hydrostatic equilibrium. Lime.
It's a really good example of how science works and how we do it, actually, because that's exactly the scientific process. You see something, you go, why is that? And Saturn's a great example. You look at Saturn and it's a oblate spheroid. It's a bit of an elongated blobby thing, but it's nearly spherical, really, first order. And yet it's got a disk of material around it. Why isn't the disk also a blob? And so that's what leads us down that journey of discovery to figure all this stuff out. So that's just how science works, and it's very fun.
Brilliant question. Thank you, Dean. Lovely to hear from you. This is Space Nuts with Andrew Dunkley and Jonti Horner.
3, 2, 1.
Space Nuts.
Our next question I really love. This one comes from Anne in Bellevue, Washington. I have a question about calcium in astronauts. On Earth, estrogen helps prevent calcium loss from bones. Do premenopausal astronauts lose less bone or regain bone faster than male or postmenopausal astronauts? Does hormone replacement therapy help postmenopausal astronauts regain bone? It's a really great question. Anne says, thanks for the interesting podcast. Appreciate that, Anne. Thanks for the interesting question. I know this isn't your area, but I know you've done your homework.
Yeah, I've done a little bit of reading. It's a fascinating question, and it's a really important question to ask because there's a lot of investigations into the impact of being in space that are going on, particularly given that there's a future where people aspire to travel to Mars and live there, or have, space stations where people live full time, go colonize the asteroids, things like that.
Yep.
It's not my area of expertise by any means. I'm not a biologist or a biomechanist. But it is something people are starting to do research into. I haven't been able to find anything about the difference between pre and post menopause or about estrogen supplements and things like that. That's a really interesting question. And it's almost possibly the kind of thing where you could find someone leading that kind of research and try and get involved if you want to. But I did do a bit of digging around. I found there is a paper that was published, I found it on PubMed, that was published a few years ago in 2014, entitled Men and Women in Space, Bone Loss and Kidney Stone Risk After Long-Duration Spaceflight, which is a slightly intimidating title. But they note there that finally at that stage, there had been enough people who identified as male and identified as female that had spent a long time in space that you could start doing a quantitative comparison. They had in their sample 33 men and 9 women who had spent long-duration missions on the space station, and their bodies had been studied when they got back, essentially. So things like bone mineral density was evaluated before and after the flight and stuff like that. And they also looked at blood and urine to look at kidney function. The missions were 50 days to 215 days flown in this millennium, so 2000 to 2012. What they found was the following, and I'll read it out explicitly. They said the bone density response to spaceflight was the same for men and women in both exercise groups, so no difference. Bone density response to flight was the same for men and women, and the typical decrease in bone mineral density, whole body and regional, after flight was not observed for either sex for people who were using the advanced resistance devices. So they were able to recover equally well. So the fundamental comment they have as the final sentence of their abstract is the responses of men and women to spaceflight with respect to measures of bone health were not different, which is really interesting.
Yeah.
It doesn't entirely talk about the importance of the hormones, but I guess the fact that women who are premenopause and men experience their bone density degradation at the same rate suggests that the elevated levels of estrogen in the women did not prevent that bone density loss. Doesn't say anything about the speed at which the bone density was recovered when they were back. So I can't really comment on that. But it reminded me more widely of, A, the risks of spaceflight, but also the amount that we don't know and the importance of getting people with different expertises involved. But also the importance of doctors and medical researchers studying women as well as men. And I know from a number of my female friends that they feel very much that a lot of medications, a lot of treatments assume that the male body is the normal one, and studies have not been carried out to such a great extent on the different impact of that same medication on the female body.
True.
And I've also heard of problems where male doctors have not been as well educated in female problems as they should have been and giving fairly rubbish responses. So, acknowledging those biases and acknowledging that I'm in a very privileged situation, but we need more research into this. NASA has on its website a statement here talking about the degree of impact on bone density. So their statement is astronauts can lose up to 1 to 2% of bone density per month in the hip and the spine. That compares to 0.5 to 1% per year in postmenopausal women and much older men on Earth. So in other words, the bone loss that you're getting while you're in microgravity in space is around twice as significant as that you experience postmenopause for women or when you become significantly older for men. And that, they say, this rapid bone loss can place crew members at risk for bone fracture and risk of early onset osteoporosis as a result of the space flight.
Yeah.
There's another study which I just stumbled across looking on this. Female astronauts, impact of space radiation on menopause. This came out a bit more recently in April 2022, and it shows people are starting to think about this. So this is a study that is looking at the impacts of the radiation environment that you experience in space on what they call the ovarian reserve, so the number of viable eggs that a woman has. And so the statement that really made my head hurt here is that data suggests that a typical Mars mission may reduce a woman's ovarian reserve by about 50%.
Whoa.
This would have consequences to a woman's reproductive capacity and more significantly decreases the time interval to her menopause. So it all reminds me, it's slightly off topic, but this was prompted by this question. I, every year, go to the Australian Space Research Conference here in Australia, which is a fabulous meeting and can be quite multidisciplinary. But a few years ago, I think possibly like 2013, 2014 now, we had a invited lecture from a doctor. It's a doctor from Tasmania who works in space medicine as researcher on the site. And it's the only lecture I've ever been to at a research conference which started with a trigger warning and a health warning. And that was basically, if there's anybody in the audience who's a bit squeamish or a bit sensitive, you might want to leave now, because this is going to be a medical talk, and you're all astronomers and space researchers.
Yeah.
And it included some fairly unsettling pictures that I won't relay in too much detail. But this doctor was talking about the future aspiration of humanity to have a permanent presence on other astronomical bodies, talking particularly about Mars. And what he was speaking to was that our science fiction view of that is that you have a population on Mars that is independent. So they reproduce and repopulate themselves. That's what we think of. And he said, it isn't as simple as that. From a doctor's point of view, from someone who studied pregnancy, he was talking about, the requirement, the importance of gravity to pregnancy is something we never think about because we're all living on the surface of the Earth at 1G. But he said it's actually the case, and I'm remembering a talk here from more than a decade ago. He spoke about how important the gravity that you are moving within is to the development of the fetus and the way that the cells know what to make and what shape to make. And he gave the example of how even a very small change from the standard atmospheric temperature and pressure and gravity can cause huge problems by talking about the invasion of the Spanish into South America back in the 1600s and the fact that the high Andes were never conquered permanently because the conquistadors couldn't reproduce there. They were just not able to be viable there. And the native people there had obviously adjusted over many, many generations. And he said that's barely any different to the conditions here. What he was going on to say was that his vision is that because of this will be so insurmountable that for a very long time, once we have a permanent presence on Mars, it would be a retirement home. It'd be somewhere that people go to after they've sowed their wild oats on Earth, that they go to spend their later years in a more pleasant environment with lower gravity, less strains on an aging, aching body. But he didn't foresee any possibility of people reproducing there. And unless we went down the incredibly dystopian worldview of having women living in centrifuges for 9 months to simulate 1G, which I can imagine would not be a very popular decision. But it ties into Mars 1, which was this attempt by, I think, a Dutch guy to make a lot of money out of sending a mission to Mars to try and get the first humans on Mars. And they ran a huge competition process for this with more than 100,000 initial applicants, and they whittled them down. But there was an Australian involved in this, guy called Josh Richards, who's a fabulous science communicator and did a lot of work off the back of this, of going into schools and talking to kids and saying, I could be the first person on Mars, ask me anything, essentially. One of the things that Josh told me that led to problems and in the end led to the breakup of his relationship with his partner as he went through this process was that he was looking at taking a one-way trip to Mars, but also that the people who were the final selected ones had to agree to be medically sterilized before they got on the trip to Mars, because they were going for a mixed crew. The mixed crew had to make their own entertainment during the travels. Yeah. And because this show was going to be delivered Big Brother style, that was probably part of the motivation for people subscribing, to be honest. The lack of understanding of the possibilities and the risks of pregnancy during spaceflight in microgravity or on Mars in incredibly reduced gravity was such that nobody could see any possibility of any viability of pregnancy. But it wasn't like they were going to send people with the medical skills to deal with traumatic problems like that on the mission. So you had to agree to either be sterilized or you wouldn't go and pick someone else, which sounds really barbaric. But it's the unfortunate reality we're going to have to deal with when we start looking at having a permanent presence off Earth rather than just going and visiting. Because if we want to have a permanent presence on the moon or on Mars, we view that inherently as humans as being a self-replicating presence. We view it as being a presence that can sustain itself. You know, so if the population of Earth got wiped out, at least we've got the people on Mars. But in order to do that, it's going to need an incredible amount of medical research to be done and incredible advances in medical technology that we just don't have yet. And what's been asked in the question here about bone density in space, about the role of estrogen in replacing the bones afterwards, on the impact of people who are past premenopausal, that all comes into it as well, because we can't just do the research, quite frankly, on old middle-aged white guys. We need to look at the diversity, not just in terms of gender diversity, but as we move forward, are different groups of people better suited or worse suited to life in space? We know that people from different cultures and different countries have slightly different physiological properties. There will need to be research done into this, and we'll need to look at people across the whole spectrum of humanity to understand it, rather than just basing everything on the first few people who went to space, who were pretty much uniformly very athletic, very well-trained, white men of a certain age. That's just one part of his subset. So it's a really interesting question. I don't have more answers to that, but really thank you for asking it. There's a lot to think about, and it does make my head hurt in a very different way to the cosmology making my head hurt thing. It's a different part of my brain that's hurting at the minute.
Yes, absolutely. I can tell you that, when it comes to studies into medicines that you referred to, my wife and I have experienced firsthand the effect of medicines that have been created and developed for men. Yeah. By default, not purposely developed for men, just developed for everybody, but based on the physiological male. I can take an antibiotic and not feel a thing. My wife can take the same tablet and she's sick for a day. Classic example of it. So I know exactly what you're talking about. There needs to be a lot more research into medicines for women to suit their physiology. Also, Anne, I can tell you that people on Earth suffer the same problems as they do in space, particularly people who are undergoing hormone therapy for cancer treatment. They lose muscle mass and bone density, and in long-term therapy can develop osteoporosis. And the solution to that is exercise. But it's a tough battle. I'm all too aware of it myself, but it's the same problem on Earth when it comes to treating cancer at the moment with some kinds of hormone therapy. But thanks for the question. Brilliant question. Loved it. Keep them coming. Our final question comes from Dean 2. Dean 2, because we had Dean earlier. Sorry, Dean 2. You became Dean 2 because you're the second on the list.
This is Aussie Dean, isn't it?
Pardon?
Aussie Dean.
Yeah, I think so. Let's find out.
Hi, Fred and Andrew. This is Dean in Redcliffe in Queensland. Can you explain why there is a fixed amount of centrifugal force measurable on an object at the Earth's equator, but its angular velocity, which is the cause of this apparent force, can only be measured relative to another object's frame of reference. What I mean is, an 80 kilogram person should weigh about 300 grams less at the equator than at the poles, and this can be measured. However, the calculation for centrifugal force uses the angular velocity of the person going around the Earth's axis, which is measured using the frequency of the Earth's spin. Where the Earth's diameter and circumference are fixed, the Earth spins once in 24 hours relative to the Sun, once in 24 hours 40 minutes relative to the Moon, and once in 23 hours 56 minutes relative to distant stars. Although these frequencies are all fairly close, they would each give different answers to the calculation, yet we can measure centrifugal force as a fixed amount. Although all objects in space are moving, I suspect that space itself does not move, even though it's expanding. So, does space-time have a fixed structure that determines direction without reference to objects within it? Thanks for the podcast.
Wow. Thanks, Dean. We sort of hinted at centrifugal force earlier, but this is a different angle on it. Boom, boom.
Boom, boom. It's an awesome question, and there's a couple of different parts to it. So I'll initially talk about the effect of the Earth's rotation on your weight. I think that's a good one in terms of the dependence on a reference frame. There isn't really a dependence on a reference frame for it because what we measure is what is actually happening. So the Earth rotates at a certain speed, and because you're moving at that speed, you've got gravity pulling you down, but the movement that you've got, the rotation, is carrying you off at right angles to gravity, and you're kind of falling around as you go around. So because you're not falling into the Earth, but you're also not escaping from the Earth because of your movement, it's as though there's a little bit of an outward force balancing gravity. That's the net result of it. So we can work this through with all the maths, and I sometimes do this derivation for my students because it's kind of vaguely elegant to get in the orbital period for things. You can do this kind of maths. What's effectively happening, though, is that you have an acceleration going on. You're an accelerating object. And because of your motion as you rotate around the Earth, you do one full lap in a certain amount of time. That means it is as though you're being pulled towards the middle with a certain acceleration, and that's the acceleration due to gravity you feel. And the faster you spin, the lower that pull towards the middle feels like it is because you're offset by the centrifugal force that you feel, which is a virtual force, feeling like it's pushing outwards by comparison. The real number you measure is based around what the acceleration on your body actually is, and that's something that's quantifiable. And that is down to you completing exactly one lap of the Earth in the reference frame of the Earth. So that's the one thing that was missing from this. We talk about the sun, we talk about the distant stars, we talk about the moon, but in reality, you're talking about in the Earth's rest frame. So you're going around in a circle around the center of the Earth. That takes you 23 hours, 56 minutes, and 4 seconds. The distant stars are just a reference point where we can see that for, but it's all relative to the position of the Earth. And so that's what gives you your 300 grams less. The sun and the moon are also moving in the rest frame of the Earth. The sun does one full lap around the Earth in 1 year. The moon does one full lap in 1 month. So that's why you've got those slightly longer times, because the Earth's got to turn a little bit more than one full revolution before the sun is directly overhead or before the moon is directly overhead. So that isn't a rest frame, that's a moving frame. That's a rotating frame, essentially. If you measure it with respect to the sun being overhead, the whole of the Earth's frame has had to rotate round in that case. It brings us on to the concepts of rest frames and how you measure them and what is the universal rest frame. That's again where it gets really, really headachy. Now, to my knowledge, it isn't thought in any of the models of space-time, but space-time is fixed and distinct from the objects within it. Rather, any object that is moving at a fixed speed and not experiencing any acceleration is in a rest frame. It's at rest locally. It's not accelerating. And so it can look out at the entire universe from its perspective, and any accelerations that it sees and any motions that it sees are what's actually happening out there. If you're in an accelerating rest frame, you are not in a rest frame by definition because you're accelerating. So a person on the surface of the Earth is accelerating as we go around the Earth as the Earth rotates. And as the Earth goes around the Sun and as the Earth orbits the center of mass of the Earth-Moon system and all the rest of it. So we're not actually in what I think is often described as an inertial frame. However, you do a lot of thought experiments that are near enough. If you were free-floating in space, away from any of the stars, you'd probably consider yourself to be an inertial frame, but even then you'd have some acceleration from the stars. There isn't really, as far as I know, and this is where we get onto the cosmology stuff, which is more woolly for me, and so I'm giving a less accurate and less good quality answer, and I apologize for that. But there isn't, to my knowledge, any universally accepted rest frame, because everything is moving and everything is accelerating and feeling the gravity of everything else. But the way that our models of the universe work is that they have this concept of space-time, but it isn't like space-time is a fabric that is physical over which everything moves that is itself fixed. Even space-time is moving and dragged around. I'm aware that this is an answer that's quickly devolving from sensible into the incoherent, and that's because this is pushing the limits of what my knowledge is. But it's also pushing the conceptual limits on which we build the foundations of stuff. And that's because a lot of the models, and particularly a lot of the way the models we use are described, we simplify things to make it clearer how everything works. So we talk about an object at rest. People explaining special relativity for the first time will talk about an object at rest and another object moving at a finite speed that is near the speed of light relative to it. And that's a great thought experiment. The reality is a lot of the time that we are so close to being in that situation that you can ignore the effects of the little bits that perturb it, unless you've got incredibly good measuring equipment. So from the point of view of, to totally switch analogies, I was watching the cricket the other night. If you imagine two cricketers and somebody running in and bowling the cricket ball, but instead of it bouncing, it just goes straight on. So it's a full toss, it's a beamer. Nasty delivery, boo, hiss, yeah, very, all the rest of it. The only thing that is going on in terms of predicting the trajectory of that ball is that it has that acceleration pulling it down. There's a little bit of air resistance as well. If the ball's spinning, you get Bernoulli effects and things that can cause it to swerve. But that ball is moving, and we can treat it as though the cricket pitch and all of the players are in a shared inertial rest frame. There's nothing else going on other than this single gravitational force pulling down. We don't have to take account of things like the Coriolis effect, which is another virtual force like the centrifugal force that is the result of the rotation of the Earth and the different rotation speeds at different latitudes. We can treat that in a local isolated case as though it is a much simpler scenario than it is, because all those other corrections are so small that they don't really impact things. What it leads to, though, is we tend to explain things using those simpler things, simpler scenarios. And that leads to questions like this, because it leads to the idea that there is something external to the Earth and the Sun and to us as observers that is in itself fixed, and that there is an absolute idealized frame of reference. My understanding is that all of our models do not argue that when you get into the nitty-gritty. It's a woolly answer. I appreciate it's probably not an ideal answer, Dean, and if that answer was not satisfactory for you, please ask Fred when he's back and get a different version. I do think this is important for anybody who's learning, actually. I say this to my students. I've got a tutorial in a couple of hours, which is why I'm thinking in this headspace. My explanations are one explanation of how things work, and they'll work for some people. But we all think about the universe differently, and there is no shame in saying that explanation didn't work for me. Let me find another.
Yeah.
It's really important. If my explanation of that, which admittedly, was probably not a perfect explanation even for me, doesn't work for you, there will be other explanations around, and it's worth asking another person to get a different perspective if what I said there didn't make sense. There is no problem with that. I will not be offended if you ask Fred in 2 weeks and say, Jonti failed to explain this. His explanation was rubbish. Tell me what's really happening, Fred. And then let him go and see what happens.
Okay, fair enough. Great question. Very deep thinking there, Dean, and thanks for sending it in. If you'd like to send us a question, you can do that on our website, spacenutspodcast.com or spacenuts.io. Click on the AMA button up the top. And you can send us text and audio questions and have a look around while you're there. You're always welcome to our website or our social media on Facebook or Instagram or YouTube if you're a YouTube follower. Thanks for your support. We've got quite a large audience on YouTube these days. That's it. Oh, we're done. I was looking for another question. Jonti, thank you so much.
That's an absolute pleasure. I obviously didn't talk too much today. So first time for everything.
you might want to look at the time ticking up here on my clock. Thanks, Jonti. We'll catch you next time. Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. And thanks to Hugh in the studio, who couldn't be with us again today because he was overproducing methane. Yeah, he'll be out of hospital soon. And from me, Andrew Dunkley, thanks for your company. See you on the next episode of Space Nuts. Goodbye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.